Welcome. Now that we have learned a little bit about the variational principle, it is finally time to put it to good use. So we will begin by studying the ground state of helium. So of course, helium is kind of close to hydrogen, but it has one more electron and one more proton. So we will begin by writing down the Hamiltonian of the helium atom, just as we did with hydrogen. Right? So the Hamiltonian in this case, well, we have two electrons that are orbiting the nucleus. So we are going to have the kinetic term, but this time there's going to be two parts, right? One for electron number 1 and one for electron number 2. So this is the kinetic part. Kinetic, or maybe just a T, depends on how you usually do it. And then we have the interactions, right? The potentials. So we are going to have interaction between an electron and the proton, interaction between another electron and the proton, and then an interaction between both electrons. So let's begin with the interactions between the electrons and the protons. So this is going to be minus E squared, right? We have both of the, so they have charge of E in the electron, but then the nucleus has 2E. So unlike in hydrogen, we are going to have a 2 here because the nucleus has a charge of 2. So we get 2E times 2. And this is of course divided by 4 pi epsilon 0 and then times 1 over R. And this is for one of the electrons, so let's label this R1. And the exact same thing is going to be true for the other electron, except it's going to be 4 pi epsilon 0 over R2. So of course we can now we can factor this and write it in the following way. So as minus this right here times 1 over R1 plus that kind of looks like a 2. R1 plus 1 over R2. And then we have the final interaction, which is between two electrons. So this time we're going to get a plus sign, and then we get E squared over 4 pi epsilon 0, right? This is just a Coulomb interaction. And then we get 1 over the distance between the nucleus and, the nucleus was before. This time it's the distance between both of the electrons. I was thinking that it didn't specify before. So R1 was, of course, the distance between the nucleus and one of the electrons. R2 is for the nucleus and the other electron. And this time we need the distance between both electrons, which is going to be R1 minus R2, absolute value. So this is our Hamiltonian. And if we look at this, so all of this is basically the same thing that we had for the hydrogen atom, right? So we had the kinetic part, except that this time we have two, but they are independent, right? They are different variables, so they're going to be solved independently from one another. And the main difference is that we have a charge of 2 in the nucleus now, instead of having a 1 before. And then we have this separate part. So this first part is basically the sum of two different hydrogen atoms, with, of course, the main difference that we have a charge in the nucleus of 2 instead of 1. So as we like to do in the variational principle, we will have to find some sort of approximation for a wave function. So noticing that this is kind of like a hydrogen atom, but with this interaction term, let's think about what the wave function would be for something like this. Well, as a quick reminder, what is the wave function for the ground state of the hydrogen atom? Again, we're going to go for the ground state of helium, so we're going to compare with the ground state of hydrogen atom, which is 1 over the square root of pi a cubed. A, again, being the Bohr radius. And then we have e to the minus r over a. So that is what we had before. Now, the main difference is that since we have now a different charge, this value of the Bohr radius, which was true for the hydrogen atom, is not necessarily going to hold for the helium atom. So let's take a look at what the value of A was, or what its formula was. So A was 4 pi epsilon 0 times h bar squared divided by m e squared. Now, we derived this some time ago, but how does this change if we have one electron and two protons instead of one electron and one proton? Well, this E, of course, came from the product of both of the charges, but this time we don't have E times E, which would give us E squared, but we have 2E times E. So we are going to get 2 times the E squared. So basically, the Bohr radius, right? It's not quite the Bohr radius, but it's analogous for the helium atom. It's going to be half of the one for hydrogen, which we simply call A. So in our new wave function, the A should now go to A over 2. So for helium, the ground state is going to be 1 over square root of pi, and then we get A over 2 cubed, which is basically A cubed over 8, right? 2 cubed is 8. And then we get E minus 2R over A. So that is the wave function for one of these states. Okay. Then the next issue is, well, what is the combined wave function? So what is the wave function of both R1 and R2? And as we know, we can separate these variables. So we can write this as through separation of variables, as we did in, well, many cases. The hydrogen atom is just one of the examples. We can write this as some wave function that depends on R1 times some wave function that depends on R2. So basically, we can write this as two of these, except that one is for R1 and one is for R2, right? Because we just have to solve the hydrogen atom separately and multiply the wave functions, which is literally this, but once with R1 and once with R2, okay? That has to be very, very clear. And it comes, of course, because we can separate. So there are no intertwined factors for R1 and R2 here. Okay, so for that reason, we simply have, as I've mentioned, two different hydrogen atoms combined. Okay, so we multiply this, we basically square it. At least this first part will be squared, so we get 1 over pi times A cubed divided by 8. But that 8 that is divided, we can simply multiply. And then we get e to the minus 2 over A. And then we get R1 plus R2, right? We are multiplying two exponentials, so the exponents add up. Okay, so this is the wave function. And this is the wave function, of course, for only this part. We are neglecting the interaction between the electrons. We are saying, okay, let's pretend that that interaction just doesn't exist. That's what we're saying by doing this. We're saying there's no interaction between the electrons, which of course isn't true. But we're going to say, okay, having to solve with the Schrödinger equation with this would be super hard. So let's just ignore it and use a variational principle with this trial function and see how close we get to the actual experimental value, which is about 79 or minus 79 electron volts. So the ground state of helium, at least experimentally determined, is about minus 79 electron volts, give or take. So we would like to get, hopefully, relatively close to that. So let's begin by looking at this thing right here. Okay, so we are going to apply the variational principle to that Hamiltonian. How did we do that? Okay, so again, the variational principle, the way we get our estimate, right? Our estimate for the ground state, we gotta take the expectation value for the Hamiltonian, but using our trial wave function, which is going to be this right here. Okay, so let's take this thing right here and apply the expectation value, or take the expectation value of the Hamiltonian. Now, you have to notice that we have the kinetic part and the potential of the hydrogen atom, as I've mentioned. So we have basically the energy of the hydrogen atom, but we have to take the charge of the nucleus to be 2 instead of 1. So to do that, I'd maybe go here as a parenthesis because we're going to need it right away. So to do that, let's remember the formula for the energy of the ground state of the, or actually the energy for the energy levels of hydrogen. So this is going to be minus, again, this is a result that we have seen previously. I'm just going to copy it. So it's E squared over 4 pi epsilon 0 squared 1 over n squared. Okay. And this, of course, is E1 over n squared. So let's take a look at this. Instead, just as we did before, this E appeared because we had one electron. So charge E in the electron, charge E in the nucleus. But this time we have charge E in the electron, charge 2E. So that means that we're going to have a 2 in here. So we can now factor this 2 out. It is going to be squared, so we have to take it out. And we're going to get 4. So in the ground state, where this n is 1, of course, we're going to get that if it before it was E1, so basically, maybe I'm going to write it as E1. So E1 new, basically, new is going to be 4 times the one for hydrogen atom. Okay? So that's also very important to know where that came from. So that means that the expectation value of the hydrogen atom that we have here and here, as I mentioned, it is a hydrogen atom, but with a charge of 2. That's going to be 4 times E1, 4 times the energy of the ground state of hydrogen, which is 13.6 electron volts. And then we have another one, right? We have one here with this. So we're going to get, again, 4 times the ground state energy. Okay, I hope that that is very clear. We simply took the expectation value of the hydrogen atom, but with a different Z. And then we have this term right here, which is going to be much harder. So we get plus the expectation value of the potential between the interaction of one electron with another electron, right? This thing right there. So of course, 4 plus 4 is 8. So maybe let's just write it as 8. So this is what we get. Now, what numerical value does this have? At least the 8 times E1. So E1 is 13.6 electron volts. So E1 is, well, minus 13.6 eV. So let's multiply it by 8. And we get minus 108.8 electron volts. Okay, so as we can see, without considering the interaction between the electrons, we are overestimating this. So, or under actually. So we need, more corrections. We need to consider this interaction. So of course, let's now dive into it. Let's calculate this beast. So expectation value of the interaction. Well, what is it going to be? Well, our wave function is going to be squared, and we know that this right here is the wave function. So outside of the integral, we'll have 8 over pi a cubed, and all of this will be squared. Then we have the constants that come from the potential, this thing over here. So we get e squared 4 pi epsilon 0. And now comes the integral. And this integral is going to have inside e to the minus 4 r1 plus r2 over a, and then divided by r1 minus r2. And this is, of course, going to be with all of our coordinates for r1 and all of our coordinates for r2. And what do I mean by all coordinates? Now, this is a notation that is used quite often, where by r1, so vector r1 basically means the vector r1, the normal one, theta 1, and phi 1. It's just a lazy way of writing it down, I will write it explicitly in just a moment. So this is what we have to solve. So now let's write it down explicitly. So I'm going to take some more space. I'm going to need it. And as you can see, this is quite a simple procedure we are doing, right? We don't have to solve any complex equations, as is the case with the Schrödinger equation. All that we are doing is we simply said, okay, let's just imagine as two different hydrogen atoms. We found some of the energy, and now we need to solve this integral. And if we solve this integral, we are done. And we get an estimate that could be relatively good. And we don't have to do the horrible, horrible job of having to solve the Schrödinger equation. I mean, just try to remember what we had to go through to solve the hydrogen atom. And this is even harder than that. So it is very, very nice that we don't have to go through that again. Now this integral. Okay, so hold on to your hats. So 1, 2, 3, 4, 5, 6. And then we get e minus 4 over a r1 plus r2 divided by r1, r2. And then I'm going to put all of our dr. So we are in spherical coordinates, so we get r1 squared, r2 squared, sine of theta 1, sine of theta 2. And then we get dr1, dr2, the theta 1, the theta 2, the phi 1, the phi 2. Okay, and now our limits. So r's go from 0 to infinity. Thetas go from 0 to pi. And our, yeah, and the, so sorry, theta goes from 0 to pi, and the phi's go from 0 to 2 pi. Okay, and what is this distance r1 minus r2? Well, that is the distance between our electrons, and we can choose an axis that where one of our electrons, let's say r1, lies on one of the axes, and then our other electron is somewhere else, so this is r2. So r1 minus r2 is going to be this distance right here. And we can orient our axis in such a way that this angle right here corresponds to theta 2. And if we do the projection of this line right here, this will of course be phi 2. It's not particularly relevant to this calculation, but just so that you can have an idea. So basically we are orienting our coordinate system so that we can use theta 2 as the angle between r1 and r2. It's just a choice of our system. And why do we do that? Because then we can use law of cosines to determine this distance, right? So that's going to be, so r1 minus r2. This is going to be the square root, that looks horrible, the square root of r1 squared plus r2 squared minus 2 times r1 r2 cosine of theta 2. And this is what we will write down here. So instead of this, we now have square root of r1 squared plus r2 squared minus 2r1 r2 cosine of theta 2. You could have done the exact same thing, but orienting it so that this angle is theta 1 instead of theta 2. You could also have oriented it along like any axis, but that would have just been, very mean for yourself. Don't do that to yourself. Okay, so now let's take a look at these integrals. So there's no phi dependence anywhere. So we can immediately solve the phi part. So we get the potential, blah, blah, 8 pi a cubed e squared 4 pi epsilon 0. This is squared, times, then we get 2 pi times 2 pi, so we get 4 pi squared. Okay, and that means that these two integrals are now gone. And now let me separate a little bit what is in here. So we can also notice that there is no dependence on theta, right? So we have theta 1 and nothing else. So we can also just integrate it right away. So the integral, so let me just write it here. So integral from 0 to pi of sine of theta 1 d theta 1, right? What is this going to be? This is going to be cosine of theta 1. We have to add a minus between 0 and pi. So this is going to be minus, then cosine evaluated at pi, it's minus 1 minus 1, cosine evaluated at 0. So we get 2, of course. So multiply by 2, and we can now get rid of this. I just wanted to make sure that there was no question where that was coming from. So basically, we solved 3 integrals already. And now we still have integral from 0 to pi. This is the theta 2 integral. So let's put, actually no, we are going to solve this integral first. So let me revert the order. So let me write the R1 integral first. So 0 to infinity. And let's put everything that depends on R1. So R1 squared dr1. There's also some more R1 parts, but we are going to be solving the integrals. This is the last integral that we will solve, so it's okay. So then we have 0 to infinity of everything that only depends on R2, which is going to be R2 squared dr2. And then we have integral from 0 to pi of, and now everything that depends on theta. Oh, I guess I could have put the exponents here actually. So actually, yeah, I'm going to do that. Wait. So e to the minus 4 over a r1 integral of from 0 to infinity of r2 squared e to the minus 4 a r2 dr2. And now comes integral from 0 to pi of sine of theta 2 d theta 2 divided by square root of r1 squared plus r2 squared minus 2r1 r2 cosine of theta 2. Of course, we cannot, we have to solve this integral first because it includes r1, r2, and cosine theta. So solving this first is going to make things so much easier. I don't know how you would go about solving something that has r squared e to the minus r and then divided by a square root of r squared minus 2r. Like, I don't know. I have no idea how we would solve something like that. So let's begin with this and hope that our way, becomes more clear as we go. And because I'm lazy, let's call this alpha or something, so we don't have to write it down. All of this, of course, including the 2. And let's call this maybe I1. And let's solve that, right? That way we don't have to write everything down again. So I1 is this integral. How do we solve it? Well, the way to go about it is that notice that we have to solve, so we integrate with respect to theta 2, and we have cosine and sine, and we know that one is the derivative of the other. So if we take some substitution of cosine and we take the derivative, we will get sine d theta, which is already up here. So that's why using u equals r1 squared plus r2 squared minus 2r1 r2 cosine theta 2, that's why this is tempting. And why did I take this as well? Because these things are simply constants with respect to theta. So if I then take the derivative, or I take the infinitesimal here, it's going to be minus. So these two will be 0, right? They don't depend on the angle. And, well, not cosine, sorry, but sine, minus sine, in fact. So the minus sign here cancels out, and we get this. And the good thing is that we can now rewrite the integral in an extremely convenient manner. So the integral I1 is now, well, I'm not going to touch the limits because I'm going to just plug them back after I undo my substitution. You can, of course, change them, but I'm too lazy for that. Okay. So up here, we have sine theta 2 d theta 2. From this part, we can see that sine, I'm missing the d theta 2. Sine theta 2 d theta 2 is simply du over 2 r1 r2. So let's write it down. So we get du over 2 r1 r2. And all of this is now divided by u to the 1/2. So basically we can write this as this times u to the minus 1/2. And now this is an integral that we should all be familiar with at this point. So let me write it as, 1 over 2 r1 r2 integral of u to the minus 1/2 du, which is simply 2 times, so 2 over 2, they cancel out, r1 r2, and then we get u to the 1/2. That when we take the derivative, we get what we had before again. And now we simply have to plug it back in. So u was this monster right there. So we get r1 squared plus r2 squared minus 2r1 r2 cosine of theta 2. And of course, we have to take the square root of this and divide it by r1 r2. So now let's evaluate it at, between 0 and pi. Okay, so this still has to be evaluated. I just didn't write it explicitly. So at pi, what do we get? We get square root of r1 squared plus r2 squared. And what else? Then we have minus 2r1 r2 times cosine of pi, which is minus 1. So the minus cancel out. We get plus 2r1 r2. And well, all of this is going to be divided by r1 r2. And then we get minus this thing evaluated at 0. And cosine of 0 is going to be 1. So this time it's going to be minus sign. So we get r1 squared plus r2 squared minus 2r1 r2. And all of this divided by, or maybe write it like this, divided by r1 r2. Okay, now notice that we can rewrite this because this is the same as square root of r1 plus r2 squared. And this is the same as r1 minus r2 squared. And of course divided by r1 r2. Okay, so now we can take the square root. And we have to consider that since this is squared, there could be maybe 2 cases to consider. So this quantity is always positive because both r1 and r2 can only take values between 0 and infinity. So this is always positive, so we can simply take the square root of this. We just get r1 plus r2. But here, it could either be positive or negative because if r1 is greater than r2, then it's positive. But if r2 is greater, then we have something negative. So we need to take the absolute value of it. So r1 minus r2 in absolute value. So there are 2 possibilities. Either r1 is greater than r2 or r1 is smaller than r2. So let's go for each one of those cases. So case number 1, r1 greater than r2. Well, if that happens, then this quantity is positive, so we don't have to worry about anything illegal. So we can just leave it like this. So basically we get r1 plus r2 minus r1 minus minus, so plus r2. So the r1s cancel out, and of course it's divided by r1, r2. And the r1s cancel out, and we get 2 times r2 over r1, r2. So basically 2 over r1. And in the other case, where R1 is smaller than R2. This time, this is going to be negative, so we have to put a minus in front. So basically, this here will be plus. So we get R1 plus R2 plus R1 minus R2. So this time, the R2s cancel out, and we get 2 R1 over R1 R2, or 2 over R2. So there are two cases to consider. So let's go back to the integral and see how this affects us. Okay, so basically, the monster that we had here, this integral right here, so we already solved this, and we know that this integral is either going to be 2 over R1 or 2 over R2, depending on which one of those is greater, right? If R1 or R2 is greater. So what does that entail exactly? So let me get rid of some of this. Okay, that's terrible. So let's see. I'm going to rewrite some of this. Of course, I'm going to leave this as alpha. This will be alpha, the first integral, which I will do nothing to just yet. And now, notice this. Our integral, the form of our integral depends on whether R1 is greater or smaller than R1. And since we are integrating with respect to R2, the endpoints of this integral depend on or they tell us what the value of R2 is. So we can write this as integral from 0 to R1, because in all of this, throughout all of that, R2 is smaller than R1. And what do we do in that case? When R2 is smaller than R1, right? So we have to take 2 over R1. So we have what we had here before. So, R2 squared e to the minus 4a times R2, dr2, and then times 2, which I can write here, divided by R1. Okay, so that's that part. And then we have integral from R1 to infinity. So it's the exact same stretch, it's the exact same borders as before, except that we took them apart so that we can consider this case by case. So now R2 is going to be greater, so we get 2 over R2. So this will be 2, and now this exact same expression, e to the minus 4a R2 dr2, but now it's divided by R2. So basically, this cancels out with the exponent here. All right, so that is where we are right now. Okay, so I'm gonna clear up some space here. So now we have to solve the integrals for R2. We can actually take this R1 outside for now at least. 2 over R1, since it doesn't depend on R2. So R2 squared. Okay. And I'm going to clean up notation here as well. So as you can see, this integral is kind of the form x e to the minus x, or x to the n, maybe let's call it. We have seen such integrals very often before, and we should know how to deal with them. Unfortunately, usually when we encounter them, we have them from 0 to infinity, and now we have them from 0 to R1 and R1 to infinity. So the formula that we have seen in the past, which tells us that this integral is simply n factorial, this doesn't quite work. Okay, because we're not going from 0 to infinity. So you could adapt that formula, but let's just go through this. Let's take the time because it is important. So actually, no, I'm not gonna write everything down again. I'm just gonna say this thing right here, and when you choose which integral to do first, in a case like this, take the one with the highest power, because in the process, we will come across an integral of this form. So if we do this first, we will have already solved that. I guess it doesn't really matter that much, but you know, if it can save you some trouble, it's good. So let's call this I1. So I1 is going to be integral from 0 to R1, R2 squared e to the minus 4a R2 dr2. So let's call u, so let's integrate by parts. So, and u will be R2 squared, du will be 2 times R2 dr2. And the v will be e to the minus 4 over a R2 dr2. And of course, v will then be the integral of this, so minus a over 4, and then e to the minus 4a R2. So integrating by parts, we have to multiply these two first. So we get R2 squared minus a over 4, and then e to the minus 4 over a R2, and all of this evaluated between 0 and R1. And then we get minus this times this, so these two. So we get, let's see, another minus sign here, so we get a plus, and then 2 times a over 4, and then integral of 0 to R1 of R2 e to the minus 4 over a R2. So we have to integrate by parts. Again, we got to something similar to before, but this time it's not squared, it's simply to the first power. So again, let's integrate by parts. Let's say u this time is going to be R2, du is going to be dr2. You may want to change the names of the variables if using u and v again is confusing. These ones are gone, we just use them temporarily, so this u is completely different, don't get confused. The v, again, e to the minus 4a R2 dr2, and v minus a over 4 e to the minus 4 over a R2. Okay, so let's plug this in for this part. But first, of course, we need to consider this. So we get minus R1 squared, plugging in this part, a over 4 e to the minus 4 over a R1, and then minus evaluated at 0. But there's an R here, so if you evaluate at 0, you get 0. Now, this is the part that is usually 0 whenever you do this when R1 goes to infinity, right? In that case, this would also be 0, but this is not the case. That's why we couldn't use the formula before. And okay, so then we have plus 2a over 4. I'm not simplifying it because there's going to be a lot of a's over 4, and it might be important to factor it out later, but it's not particularly important. You can simplify it if you feel like it's, you know, annoying you or something. Okay, so now multiply these two. So we get minus R2 a over 4 e to the minus 4 over a R2 between 0 and R1 minus another minus, so we get plus integral from 0 to R1, and then we get, I'm doing this by the way, a over 4 e to the minus 4 over a R2 dr2. Okay, so this is going to be the same. E to the minus 4 over a R1, and then plus 2a over 4. Okay, now we evaluate this at R1. When we evaluate it at 0, it's going to be 0 again. So we get minus R1 a to the 4, a over 4, sorry, e to the minus 4 over a R1. And then we get minus, when we integrate this, a over 4 squared and e to the minus 4 over a R2 evaluated between 0 and R1. And let's evaluate it right away. When we evaluate it at R1, we simply get an R1 here. We simply get R1. And we evaluate at 0, we get minus this thing, which also has a minus, and the exponential will be 1. So we get this. Okay. So this is integral numero uno, this one right here. And now we will have to integrate this, which is integral 2. So I'm going to write it here. So integral 2. And maybe I should put I1 here to make sure that we know that it's this. Integral 2 is going to be, not counting this 2, of course. So this is integral from R1 to infinity of R2 e to the minus 4 R2 over a dr2. Okay, and that is basically the same as this, except that the endpoints, oh, I missed this before, except that the endpoints of the integral are different. So this was the result from before. So let's write down exactly the same, but of course changing the endpoints. You can of course just calculate it again, but you know, why do it twice? Minus 4a r2 between r1 and infinity. And then we get plus integral between r1 and infinity of a over 4 e to the minus 4 over a r2 dr2. Okay, so here the first part will go to 0. When r2 goes to infinity, this whole thing goes to 0. And then we have minus evaluated at r1. So we get r1, right? The minus cancel out. A over 4 e to the minus 4 over a r1. And then we have this part right here, which will give us minus a over 4 squared e to the minus 4a r2 between r1 and infinity. So again, let's evaluate this right away. So when it goes to infinity, this entire thing goes to 0, just as before. And when it goes to, and in the other case, when it goes to r1, well, then it doesn't go to 0. So in that case, we will have to count. So this will be positive, and this will be r1. Okay, so this is our other integral. So now we have both results. So we have the result for this integral and for this integral. So now let's copy it down here. So let's see. Our potential, VEE, this was integral from 0 to infinity of r1 squared e to the minus 4 r1 over a dr1. And then came everything that we have, right? Yes. So it begins with 2 over r1. So 2 over r1. And now comes integral number 1, which is this part right here. Wait, why is it? It feels like it's out of focus. Okay. So integral number 1 is this right there. So that's going to be minus r1 squared. Yeah, I'm not going to do anything just yet. I'm just going to copy it. 4a r1 plus 2a over 4 minus r1 a over 4 e to the minus 4a r1 squared e to the minus 4a r1 plus a over 4 squared. And then we still need the second integral. So maybe let's end this. Wait, how many? I guess I should have used a different kind of parentheses at some point. It's okay. So now plus 2 times the result from I2. So then plus 2 times, I'm going to use this parenthesis now, this part right here. So 2 times r1 a over 4 e to the minus 4a r1 Wait, I'm missing my alpha, by the way, right? Yeah, I almost forgot to write down alpha. Okay. So R1 A over 4 e to the minus blah, 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 plus A over 4 squared e to the minus 4 over A R1. Phew. Okay. So we can do a few things. We can factor out the 2, right? So there's a 2 multiplying both sides. We can just factor it out. And then we can multiply through by this R1. So this R1 right here, we can simply multiply through. Let me double check that I did it correctly. I think it is. Yeah, okay. So let's multiply in by R1. Actually, I'm gonna just take the parentheses because I need to simplify a lot. So I don't want to write down this entire thing. So I'm just gonna take the parentheses and then I'm gonna plug it back in. So the parentheses, I'm gonna get minus R1 A over 4, and I can probably factor out A over 4, right? Yes, so I'm gonna factor out A over 4 from everywhere. So I'm just gonna write it as A over 4. And then we get minus R1, so it's this part, e to the minus 4a R1 plus, actually, well, I'm going to get a minus here. So then comes this first term. So we get minus 2 times the a over 4 is outside. And this R1 will be cancelled by this. So we get a over 4 e to the minus 4 over a R1. Now we multiply the next one here. So we get minus again 2 times a over 4 squared. And now I have to divide by R1. And e to the minus 4a over R1. And in this final term here, I'm going to get plus 2 times a over 4 squared, and I have to divide by R1 again. Whew. Okay, so that's the first part. And then we get these exact same things. So basically plus R1. I have to factor out a over 4. So R1 e to the minus 4a R1 and plus a over 4 e to the minus 4 over a R1. Okay. Now let's see if we can simplify this somehow. So we have R1 e to the minus 4a R1, which is exactly the same as here. So bam, bam. Then we have, let's see. Let's see, is there anything else we can simplify? This and this. We have the exact same thing, except that here there's a 2 and here there's a 1. So this will get rid of this 2 right here. Okay, so basically this entire term will be a over 4. And then we get minus a over 4 e to the minus 4 R1 over a minus 2 over R1 a4 squared e to the minus 4 over a R1. And then I have this plus 2 R1 a over 4 R squared. There we go. Okay, what else can we do here? Well, we can clearly also factor out another a over 4. So we get a over 4 squared. Now you can see why I didn't want to multiply through when we had 2 times a over 4 before, because we get a lot of this. And we also have this exponential. So let's also factor out inside by this exponential. So e to the minus 4 R1 over a. And there's also a minus sign in both of these. So a minus sign. And here we already took out the a over 4. We already took this. So we get 1. And then this one we get plus 2 over R1 times a over 4. And now we can just simplify it. So we'll just write it like this. Actually, So A over 2R, right? A over 2R1. A 2R1. Yes, okay. And then we have this part right here. So that's going to be, one of these A over 4 is going to be outside. So we get 2 times A over 4. So A over 2R1. Phew! Okay. This is the squared bracket. So instead of this monster that we had right here, instead of this, we are now going to have, and I'm going to move this dr. Instead of that, we will have A over 4 squared, and then, well, this entire thing, you know. We can actually even factor out A over 2R1. So let's factor it out just to make sure that it's even. So I'm going to write it down here just to make sure that you know what I mean. So we can simplify this even further if we write it as A over 4 squared and then factor out A over 2R1. Because in that case, we get, so this thing will be 1 minus the exponential. And this part here will be 1. So we get something plus 1. And for this to, so that we, in order for us to be able to factor this out, we need to write this as 2R1 over A. That way, if we multiply through, this is 1 once again. Okay, so this thing here is going to be A cubed and 4 cubed times 2R1, basically. Okay, so let's go back here. So the entire term in square brackets is A cubed, right? Wait, it's not, sorry, it's not 4 cubed, it's 4 squared, because it was squared before, yeah. So A cubed divided by 4 squared times 2 and times R1. And then comes the term in brackets, which is 1 minus e to the minus 4 R1 over A times 2R1 over A plus 1, dR1. Now let's get rid of this. Whew, okay, breathe in deeply. We are making progress. We are making progress. All of this is simply trying to solve this damned integral. That's kind of all that the variational principle does, or at least that's what we have to do. Okay, let's take all of our constants outside. So this 2 will be cancelled out by this. So we get A cubed alpha 4 squared. This R1 will cancel out this. And now let's multiply through by R1. And let's separate each one of these terms. So we get, in the first term, we get R1 times e to the minus 4 R1 over A, right? This one. Then we get this part, which will be minus, then we have 2 R1 squared over A and e to the minus 8 R1 over A, right? Because we have to multiply both of the exponentials together. So we use this, yes. And finally, this part right here, we get minus R1 e to the minus 4 R1 over A. And that's it, right? There's nothing that I'm forgetting. So we get R1. Oh, yeah, there's a mistake. It's 8, it's not 4. So minus 8 R1 over A. So now these integrals, they are indeed of the form of integral from 0 to infinity of x e to the minus x, or x to the n, which we know is n factorial. The problem is that we don't have quite this to the minus x, but what we have is this times something, right? This b. And in that case, as we have seen before, I'm going to show it anyways, but I'm just going to write it quickly and then show it. this is going to be times 1 over b, and this is going to be to the power of n plus 1, basically. Okay, and I'll show you why this is. So maybe let's go with this case, which is the highest order one, just so you get an idea. We need to change the form of this. So we have integral from 0 to infinity of r1 squared e to the minus 8 r1 over a dr1. So now let's use x. X is going to be 8 r1 over a, because we want this to be e to the minus x. So this means that r1, of course, this is going to be ax over 8. So dr1 is going to be dx times a over 8. So this integral will now become, well, r1 squared is gonna give me a8, so a over 8 squared, and then from dr1 we are gonna get another a over 8, and then we get integral from 0 to infinity of x e to the minus x dx. Okay, so that's where this thing comes from. So if the exponent is 8 over a, we get a over 8, so we flip it, and then it is to the power of this thing, so 2, and then there's another one, which comes from the dx or dr. Okay, so we're going to use that formula or that principle in this part. Wait, I didn't mean to do that, or that. There. Okay, so going back to this, right, this part. So we get a cubed alpha divided by 4 squared, and then we get this thing right here, n is equal to 1. 1 factorial is 1. And this thing, so our 1 over b, which is going to be a over 4, this is going to be to the n plus 1, which is 2, right? N was 1. Okay, next one, here. We have a pre-existing minus 2 over a, and then we get 2 factorial times 2, right? 2 factorial is 2, times a over 8 cubed, right? Squared plus 1. And then we get minus, and there's an r1, so we get simply a over 8 squared. Okay, so this a cancels out partially with the exponential, or the exponent, sorry, and we can factor out a few things. So let's factor out a squared, and then we are left with 1 over 16 minus, and then here we have 1 over, this is 8 times 8, which is 64, times 2, because one of the 8's canceled out with this 4. And then we get minus 1 over 64. So in order to get the common denominator, a to the 5th alpha 4 squared. So common denominator, what do we have? We're going to have to get to 128. So that means multiplying this by 8, right? For, I think so, right? So 16 times 4 and then times 2, which is 8. Yes. So we get 8 minus 1 minus 2 over 128. So all of this is 5 over 128 times a to the 5th 4 squared and alpha. But what was alpha? Alpha was, and what was it again? Here, 8 pi a cubed. So it was 8 pi a cubed squared, and then we got e squared 4 pi epsilon 0. That's what alpha was. Okay. So just as a reminder, this is this stupid expectation value that we're looking for, okay? We're still working on that. We haven't gone anywhere. So we can now begin trying to simplify a few things. Wait, Wait. Did I forget something? Yes, I didn't include everything. Yes, I almost forgot to include this 4 pi squared times 2. So I still need to include that. So 4 pi squared times 2. Which, in case you don't remember, that came from the integrals of phi and of theta 1. So 4 pi squared times 2. Okay, so let's begin simplifying. Let's see. So this pi squared will cancel out with this pi squared. Then we have a to the 6th here and a to the 5th. So we get 1 over a. So this and this are gone. Then we have, let's see, this is, so this 4 will cancel out with this. And I think I'm going to just write it. Let's see, this is 64 and this is 64 times 2. So this cancels out with this. And this 2 cancel out with this 2. Okay, so we are left with 5 over 4. There's nothing left here. And then e squared 4 pi epsilon 0. Okay, now what was a? A reminder, a, as we saw before, is 4 pi epsilon 0 h bar squared over m e squared. So if we plug that in, we get, well, 5 over 4, this was already there. And then 1 over a, we get m e squared over 4 pi epsilon 0 h bar squared. And then we have e squared 4 pi epsilon 0. But remember that E n, as we saw before, this is minus m over 2 h bar squared times e squared over 4 pi epsilon 0 squared times 1 over n squared. But of course, we're dealing with the case n equals 1, so we can just set the n's to be 1. So as you can see, we have m e squared squared. We have 2h bar if we take a 2 from this, right? So 4 is 2 times 2. So we take one of those 2's. And then we have 4 pi epsilon 0 squared, and we have h bar squared. So basically, we have 5 over 2, and we have to consider a minus sign, so minus. And then we have E1. Right, so we used all of this, we are only left with that part. And what is E1? E1 is, of course, minus 13.6. So we get 2.5 times 13.6. And this is going to be 34 electron volts. So that is the contribution from the interaction between both electrons. So now let's go back up, quite a way up here. So before, we were talking about the fact that the experimental energy for the ground state of the helium is minus 79 electron volts. What we saw before, right, is that what we're doing right now was, or our guess is 8 times the ground state of hydrogen, which is minus 108.8 electron volts. Actually, I'm going to go to the side. So theoretical for helium, this is minus 79 electron volts. And before, using variational principle, we saw that the energy of that we are now testing using our trial function was how much? Minus 108.8. So minus 108.8 electron volts. And now we have to add 34 electron volts on top of it. So our guess for this, or our estimate rather, is minus 74.8 electron volts. So we definitely overestimated as it happens. But considering that our trial function was not really too refined, it wasn't anything too crazy, we still got pretty close. Okay, and all that we did was we wrote down the Hamiltonian and said, oh, this is basically two electrons together that don't interact. So basically two hydrogen atoms, and then one interaction term. And we took the trial function for this separate hydrogen atom, but with a modified nucleus with a charge of 2 instead of 1. And we used that. And we basically took this interaction as our perturbation for the variational principle. And sure, we had some annoying integrals, right? We had to solve this integral, but we didn't have to solve the Schrödinger equation, and we got a pretty close approximation. And in the next video, I'm going to use a better trial function, right? We're going to actually think about the situation and come up with a better trial function, and we will get much, much closer to the actual answer. So I hope I'll see you there. If you enjoyed, make sure to leave a like on the video, comment. It really helps me out a lot. It doesn't cost you anything. And always consider subscribing and maybe sharing the video to your classmates if you think it could help. So thank you very much for watching. I'll see you in the next video.